Have you ever stopped and wondered how your computer actually thinks? I mean, really thinks. How does it go from just being a box of circuits and electricity to letting you play games, surf the web, or write an email? Well, today we're going to pull back the curtain and look at the secret language of computers, the fundamental building blocks of, well, everything digital.
It sounds kind of crazy, but here's the truth. Deep inside your computer's processor, there are literally billions of microscopic switches called transistors. Each one can either be on or it can be off. And that simple two-state system, that's the starting point for the entire digital universe.
In this on-off state, well, that's where a language called binary comes in. It's super simple. A 0 means a switch is off, and a 1 means a switch is on. Every single thing your computer does, every photo you see, every song you hear, is, at its very core, just a massive, mind-bogglingly fast sequence of zeros and ones. It's a universal language built on the simplest alphabet you can possibly imagine.
Okay, so we can store stuff. A 1 here, a 0 there. Big deal, right? But how do we get from just storing information to actually doing something with it? How does a computer take those bits and make decisions, do math, and turn your clicks into actions?
Well, this is where the magic really happens. The answer lies in these incredible little things called logic gates. You can think of them as the true decision makers of the digital world, the microscopic brains behind all the binary.
So what is a logic gate? Just think of it like this. It's a tiny little machine with one very simple, very specific job. It looks at the ones and zeros coming in, and based on a single, unchangeable rule, it decides whether to send out a 1 or a 0. That's it. That's all it does.
And here's the wild part. Almost all of modern computing, the whole shebang, can be built from just a few of these simple rules. So let's start with the three most fundamental gates of them all: not, and or.
First up, we've got the NOT gate. Honestly, it's the easiest one to get. It's basically the opposite day gate. It takes just one input and flips it. You give it a 1, it spits out a 0. You give it a 0, it gives you back a 1. Simple.
And we can map this out with something called a truth table. Don't let the name scare you. It's just a simple scorecard for the gate, kind of like a cheat sheet for what it does. As you can see, the table shows its entire job. Input is 0, output is 1. Input is 1, output is 0. That's the whole story. All right, next is the AND gate. Now this one's a bit of a stickler for the rules. It takes two inputs, and as its name suggests, it's very demanding. It will only give you a 1 on the output if the first input and the second input are both 1. Anything else, and it's a no-go. And if you look at its truth table, you can see just how strict it is. 0 and 0? Nope, that's a 0. 0 and 1? Still 0. 1 and 0? You're still getting a 0. Only in that one single case, where both A and B are 1, do you finally get that 1 as the output.
Now, let's compare that to its much more chill cousin, the OR gates. This gate also takes two inputs, but it's way easier to please. It'll give you a 1 on the output if input A is a 1, or if input B is a 1. It really doesn't care which, as long as at least one of them is on. You can see it right here in the table. The only way you're ever going to get a 0 out of an OR gate is if both of its inputs are 0. Any little hint of a 1 coming in on either line and boom, the output is immediately a 1.
Okay, so those are our basic Lego bricks, but the real fun, the real power, starts when we begin snapping them together. This is where a few simple rules suddenly start creating some really complex and interesting behavior.
So, let's do a little experiment. Imagine we take our super strict AND gate, the one that only outputs a 1 when both inputs are 1, and then we immediately feed its result into a NOT gate, which, remember, just flips everything. What do you think we'd get?
We actually get a brand new gate. And this little combination is so common and so incredibly useful that it gets its very own name, the NAND gate, which, you guessed it, is just short for not and. Its job is to do the exact opposite of what an AND gate does.
In this comparison really makes it clear. While an AND gate gives you a 1 only when both inputs are 1, the NAND gate does the complete opposite. It outputs a 0 only when both inputs are 1. For everything else, it's a 1. It's a perfect inversion.
And you probably saw this coming. We can do the exact same trick with the OR gate. You take an OR gate and feed its output into a NOT gate, and you get a NOR gate, or not OR. It only outputs a 1 in the single case where a regular OR gate would have output a 0.
So this is all cool, but what's the point?
Well, the point is that we can now use these building blocks to solve real, specific problems. So let's take a look at a classic example.
Here's the puzzle for you. We need to build a circuit that will only turn on if exactly one of its two inputs is on. Not both and not neither, just one. So a 0 and a 1 should work, a 1 and a 0 should work, but two zeros or two ones should stay off. How would we build that?
Well, using the gates we know, you could reason it out. Logically, we want the situation where A or B is true, and we also need the situation where A and B is not true. I mean, it works, but yikes, look how clunky and complicated that circuit starts to get.
Thankfully, there's a much cleaner, much more elegant way to do this. This exact problem is so common that it also gets its own special, purpose-built gate, the exclusive OR gate, or XOR for short. Its whole reason for existing is to solve this specific problem.
And just look at its truth table. It's the perfect picture of our solution. It only outputs a 1 when its inputs are different from each other. That's why we call it exclusive. It specifically excludes the case where both inputs are the same.
Okay, so let's zoom out for a second and just appreciate what we've uncovered here. We've seen how a few ridiculously simple rules can be combined and chained together to create more and more specific and more powerful behaviors.
This handful of gates we've talked about, NOT, AND, OR, and their cousins, NAND, NOR, and XOR, that's pretty much it. These are the atomic units of logic. By combining millions and billions of these in incredibly clever ways, we build circuits that can do math, store memories, and ultimately run every single piece of software you have ever used.
So the final thought I want to leave you with is this. If the entire digital universe, from the smartphone in your pocket to the servers running the internet, is all constructed from these few, simple, undeniable rules of logic, what other complex systems, what other amazing things could be built from equally simple foundations? It's a really powerful idea when you think about it.